Hello, welcome to Econometrics Melody. In this video, we'll discuss about the negative binomial distribution. Before that, let us look some of the useful functions. Exponential and logarithm are inverse to each other. That is why they cancel out each other's effect, and we are left with factorial 5 in this case and gamma 6 in this case. And we want to establish a fact that gamma 6 is equals to 5 factorial. That is, gamma n is equals to n minus 1 factorial. That is why gamma 8 is equals to gamma 9 is equals to 8 factorial, gamma 8 should be equal to 7 factorial, gamma 12 should be equal to 11 factorial, and we cannot calculate the factorial of any decimal values while we can calculate the gamma of any decimal values. Now let us see another useful function, combination, and let us run all of them and explain what does it mean. So there is one unique way in which we can select nothing out of 3 objects, and there are 3 unique ways in which we can select one thing out of 3 objects, and there are 6,435 unique ways in which we can select 7 things out of 15 objects, and 167,960 unique ways in which we can select 9 objects out of 20 objects. Now let us look some of the formulas of negative binomial distribution, and we'll explain some of them, and we'll calculate the CDF and PMF associated with it. The mean is calculated by using this formula, where 1 minus p is the probability of failure, and p is the probability of success, and n is equals to the nth success. The variance is given by this formula, and we can express it in terms of mu divided by p, because n 1 minus p divided by p is equals to mean. So this is equals to mean by p, and as p is in between 0 to 1, the variance is always greater than mean. That is why we use negative binomial distribution in a situation where variance is greater than mean. Now let us say the probability mass function. Negative binomial distribution is a discrete distribution, and the calculation of probability mass function is very easy. Combination of k plus n minus 1, k comma k, and 1 minus p, it is the probability of failure to the power number of failures, and probability of success p to the power n. And this is very simple. K plus n, where k is equals to the number of failures, n is equals to the nth success, and minus 1, we deduct 1, meaning thereby we ensure k failures, where p is the probability of success in each trial, and n is the nth success, and k is equals to number of required failures before getting the nth success. Now let us go to the CDF, and the CDF, we calculate the CDF negative binomial distribution by using this formula or this relationship. CDF is actually the regularized incomplete beta function, and regularized incomplete beta function is further equal to incomplete beta function divided by the complete beta function. And once we divide the incomplete beta function by the complete beta function, then that is what we mean by regularized incomplete beta function. And complete beta function is when we integrate from 0 to 1, and incomplete beta function is when we integrate from 0 to certain values. So if we integrate from 0 to 1, that is a complete beta function, and if we integrate from 0 to some other values, that is incomplete beta function. And the complete beta function can further be expressed in terms of gamma function by this relationship, where a and b are the parameters. So a and b are the parameters. So this is the complete beta function, which further is equals to gamma a into gamma b divided by gamma a plus b. And the gamma function can further be expressed in terms of its integral form in this way. We integrate from 0 to infinity, and for this z, we take e to the power z minus 1 and e to the power minus t, and we integrate with respect to dt. This can be further boiled down to gamma z is equals to z minus 1 factorial, and z minus 1 factorial can be written as z minus 1 into z minus 2 factorial. And from this relationship, z minus 2 factorial can further be written as gamma z minus 1. So gamma z can be written as z minus 1 into gamma z minus 1, which is equals to z minus 1 factorial. Now let us see the regularized incomplete beta function certain identity. If we want to integrate from 0 to p, then we use this parameter n is a and k plus 1 is b. And if we want to integrate from 0 to 1 minus p, then we switch the place of these parameters. Now k plus 1 at first and n, and the sum of these two will be equal to 1. Now let us explain our CDF. We are integrating from 0 to p. That is why we take this. A is our n and b is our, the parameter b is our k plus 1. That is why we raise t to the power n minus 1 and 1 minus t to the power k plus 1. Here n and k plus 1 are the parameters, and this portion is our incomplete beta function divided by this complete beta function. We have taken it from this relationship. Our parameters are k plus 1 and n, and we take gamma a to gamma b divided by gamma a plus b. Now from the regularized incomplete beta function identity, from this relationship, we see that if we want to integrate from 0 to 1 minus p, then we take 1 minus the earlier one, and we need to do 1 minus and the parameters if we want to take the probability 1 minus p, or the failure rate over here, the probability of failure. So we write 1 minus, this is again an incomplete function, and divided by the complete beta function. And this is what we see over here at the first stage. Incomplete beta function divided by beta function is equal to the regularized incomplete beta function, and we'll see this by the help of example as well. Let us now calculate the CDF, cumulative distributive function of negative binomial distribution, and we have this formula n binomial. This is the Stata function to calculate the CDF of negative binomial distribution, where n k into p, n k p. So n is nth success. So we need, what is the probability of getting third success after 5 failures if the probability of success is 0.3, and we can calculate the same value by the help of binomial distribution and incomplete beta function. And this one, the fourth one, is the relationship of incomplete beta function, the identity. And the fifth one, we have used the incomplete beta function, we have used the integration, and this is the complete beta function. So, and we have calculated this integration by the help of function, quadrature function of Mata in Mata. So let us see this, and all of them should have the same value. And it's success after 5 failures when the probability of success is 0.3 in case of negative binomial distribution. And in terms of binomial distribution, we write n plus k, so 5 plus 3, 8 over here, and the k is the failure, and the probability of failure is 70%, because 30% is the probability of success. Now in terms of incomplete beta, the first parameter a, which is the nth success, the second parameter b is equals to k plus 1 and the probability of success. And if we want to subtract it from 1, then we switch the parameters. Here first we take b and the parameter a. When we compare it the above one, we take b, a, and we take the probability of failure, which is also explained here. Now let us, all of them, they yield the same value. Now let us see it by the help of the graph. And n binomial CDF, this is the user written program, we have written it. So, and we will explain it, and the probability that we get over here is nearly 45%. And let us see it. So the probability of third success after 5 failures, given the probability of success is 30%, is equal to this value, which is nearly equal to 45%. Now let us move to another example. This time we are going to increase the success rate from 30% to 40%. The probability of success is 40%, and we want to find what is the probability of getting third success exactly after 8 failures. And we have calculated it using the negative binomial, and incomplete beta function, as well as the incomplete divided by complete beta function. So this is how we calculate the CDF of negative binomial distribution. And let us see what is the probability. We get the probability is 88%. So the probability of getting third success exactly after 8 failures is 88%. Now let us say it by the help of graph, CDF graph, and this is again a user written program. And let us see whether we get 88% or not. So for after 8 failures, and the probability of getting third success exactly after 8 failures 0, 1, 2, 3, 4, 5, 6, 7, 8 somewhere over here. And if we draw a straight line, then it is nearly 88%. That's fine. Similarly, we can put any values over here like nth success and the probability of success. Now we have increased the probability of success. Once we increase the probability of success, the number of failures or the span for the number of failures should decrease, and this is what we get. The ladder nature of the graph indicates that the negative binomial distribution is a discrete distribution. Now let us calculate the negative probability mass function of the negative binomial distribution, and this is the formula: n plus k minus 1 and k into probability of failure to the power number of failures and probability of success to the power success, nth success. And this n binomial p, this is the Stata function in order to calculate the PMF of the negative binomial distribution. And when we run it all together, we see the same value. It's 0.9%, 9.5%. And let's see it by the help of graph. This is again a user written program that depicts the negative binomial distribution. And let us see at 0.5. And if we look at this 0.5, after 5 failures, what is the probability of getting third success after 5 failures when the probability of success is 40%? And here 8.5, and if we look at it, this value should be somewhere 9%. Now let us see another example in which we increase the probability of success to 40%, and let us see what do we get. Both of them should yield the same result. Now this time the probability of getting fourth success after 5 failures has increased to 10%, 10.45. So once we increase the probability of getting the success rate also increases, which is obvious. And let us say it by the help of example 0.5 again. And if we concentrate on this, and this has increased to nearly to 10%. And similarly, we can provide any other inputs for n and probability of success. So we are here wanting 12th success. What is the probability of getting 12th success? If the probability of success is 0.5, we have increased the probability to 50%. And at the backdrop, we have this the normal distribution and this later kind of graph. This is the graph for the binomial distribution, negative binomial distribution. So the probability of getting 12th success after so many failures. So after 10 failures, this is the value. It's nearly 9% or something, and so on. Similarly, let us say another example. We have now increased nth success to 20 and the probability of success is 50%. And what is the nature of the graph? The graph is almost like a normal distribution, because at the backdrop we have a normal distribution. So we can say that if we increase this nth success, then gradually we will get the normal distribution. And if the probability of success increases, then this range or the span for the failure, it decreases, and we will see it in the other examples. Now let us draw the binomial negative binomial distribution, and we're going to draw the negative binomial distribution for getting the third success, and the probability of success is 30% against so many failures. And let us see, we'll track them actually: 0 success, 1, 2, and so on. So it will ultimately show the graph up to 30th success, sorry, 30th failures. We have drawn the probability mass function of negative binomial distribution for getting the third success if the probability of success is 30% after so many failures. So nearly after 20th failures, the probability is declining to 0. And let us see another example. Now let us increase the probability of success and the probability of getting third success when the probability of success is 50%. This time the range of failures should decrease, and it is a histogram. It gives a feel of a histogram. As the probability of success has increased to 50%, the graph will meet 0 very early. Nearly after 14th failures, we get all the values 0. That is why the span or this range of the failures, it has decreased. Nearly after 13 failures or 14 failures, all the values are 0. So it is very obvious, because if the success rate has increased, the number of failures should obviously decrease in a trial. Now let us track the nth success. We are going to draw the negative binomial distribution for ranging from 1 to 6 success subsequently, and the probability of success is 10%. And let us see the nature of the graph for 1 success, for 2nd success, for 3rd success, for 4th success, and the one is 5th success, and the last one is for 6th success. So the last one, this in red or red color, we'll see that this is the graph for the negative binomial distribution graph when the probability of success is 10%, and we are going to get the 6th success after so many failures. Now, is the probability of success if the probability of success will increase, then this span of failures, it should decrease. That is what we are going to show in the next one. So let us now increase the probability of success to 20% and see what happens for 1 success, for 2nd success, for 3rd success, and 4th success, 5th success, and then the 6th success. So this one, if we compare it with the earlier one, we see that the span of the failures, it has decreased significantly. And it is obvious that if the probability of success increases, then the number of failures before encountering the required success, it decreases. This is what we have enforced. Now let us again repeat the same process. We are now simulating the graph from 3rd to 12th success, and we have increased the probability of success, and this is more a bell-shaped curve. This is span of failure, it should decrease significantly. Is the value of nth success increases, in this example from 3rd to 12, we see that the nature of the graph is more a bell-shaped curve. And then if the probability of success increases, the span of failure, it decreases. Now let us track the nth success across probabilities. Let us draw the nature of the negative binomial graph across the possible probabilities. And if the probability of success increases, the span of failure decreases. That is why we get the new graph with the lesser failure span, and it is for 35%, for 55%, the new graph for 65%, and for 75%, for 85%, and for 95%. 95%, it's almost success. That is why we get a single line over here. And as the probability of success increases, we see the graph, it's the span of failure, it has decreased. This is what we want to demonstrate by the help of these examples. And let us see, is the nth success increases, this time we have taken 6 to be 60 and the probability of success is 50%, we get more of a normal curve or the bell-shaped curve. At the backdrop, we have drawn a normal distribution with the mean and variance equal to the mean and variance of this negative binomial distribution, and they are nearly coinciding. Here our nth pass or nth success is 60. Let us reinforce this once more, and we are ranging the nth success to range from 30 to 40, and we will see the graph, and the probability of success is 40%, and we see the graph is more like a bell-shaped curve, and as the nth success increases, it will ultimately coincide with the normal distribution. We have seen it in the earlier example or the earlier graph, 47, and the nth success is 38, and the nth success is 39, nth success is 40. So the nth success, it began from 30 all the way to it indeed it nth success is 40, and as the nth success increases, the graph is more of a bell-shaped curve. And let us reinforce this once again. Now we are taking the nth success to be 90, and across all the probabilities we are going to draw it, And we will see that if the probability of success increases, the graph is more of a bell-shaped curve. In fact, it will coincide with a normal curve. So we see the graph as the probability of success is increasing, it's the range of failure decreases, as well as the graph is getting more of a bell-shaped curve. Now let us say the area graph of the negative binomial distribution. And these are the usually written programs, and we have written it. These are useful for the hypothesis testing. At the backdrop, we have a normal distribution with the mean and variance equal to this binomial distribution mean and variance. And we are wanting to have the ninth success after so many failures, and this is the nature of the negative binomial distribution. And if our null hypothesis is that k is equals to 6, and our alternative hypothesis for one till test k is less than equal to 6 or k is greater than equal to 6, then based on our situation or our condition, we make the hypothesis testing, we come into the conclusion. So if our alternative hypothesis is k is less than equal to 6, then the value is 5%, which is indicated by this pink region over here. And in this situation, our alpha value is 5%, as well as the p value for this condition, alternative hypothesis k is less than equal to 6, is also equal to 5%. So we cannot make any decision. But if our alternative hypothesis is this one, k is greater than equal to 6, then the area or the p value is 97%. So we see that this yellow region, it is representing the 97%. So this k is equal to, inclusive of the probability of 6, k equals to 6, we get this 97%. Now in this case, as this value is greater than 5%, so we fail to reject the null. For this region, for this alternative hypothesis, we have drawn this binomial distribution assuming that the null hypothesis is true, and for this condition k is greater than equal to 6, the region covers almost most of the region of the null area. So that is why we fail to reject the null in this case. But in this case, when k is less than equal to 6, it is 5%, which exactly coincides with our alpha value. That is why we are in an indecisive situation. Now let us see another example. This is useful for the hypothesis testing. Now towards the right side, we are going to get the 5% area. So at the backdrop, we have a normal distribution with the mean and variance equal to the mean and variance of this binomial distribution. Now our null hypothesis, it will be k is equals to 28, and our alternative hypothesis, either k is less than equal to 28, or either k is greater than equal to 28, or k is not equal to 28. So we are not talking about the two till test, we are only trying to depict the example of one till test. So again, we are divided into two situations. For this alternative hypothesis, k is less than equal to 28, it covers 96% of the area, including the value of k equals to 28, and this covers the 96% of the area of this graph. So this graph is on behalf of the null hypothesis, assuming that null hypothesis is true. So for this situation, this entire region, it belongs to the null hypothesis. It is greater than 5%, so we fail to reject the null in this case. But if our alternative hypothesis is k is equals greater than equal to 28, then we come out of this area. So it's nearly 5%, which coincides with our alpha value. In this situation, we are indecisive. Maybe we'll have to take another sample and again carry out the test. So this is the basics of understanding our how to reject or accept, how to reject or fail to reject the null hypothesis. Now let us see another example, and binomial area. So in this condition, again, our null hypothesis is k is equals to 2, and our alternative hypothesis, one till test, for one till test, our alternative hypothesis would be k is less than equal to 2 or k is greater than equal to 2. And as per our graph, if we see this area, it covers almost a major portion of this binomial distribution. And for this situation, we fail to reject our null hypothesis, and in this area, it is only, I guess, in this side, for the condition less than equal to 2, it is less than 5%. So we can say that this region does not belong to this negative binomial distribution. So we can reject this null. Maybe this portion does not belong to this null region because the binomial distribution is created assuming that the null hypothesis is true. It is less than 5%, so we reject the null. And for k is greater than or equal to 2, we lie in the area of null. That is why we fail to reject the null, because the probability is greater than 5%. And let us see another example. And this is again a user written program, and we can manipulate the nth success, k failures, and the probability of success. And let us see what kind of result do we get. And we are trying to depict the situation in the graph. At the backdrop, we have a normal distribution with the mean and variance equal to the mean and variance of this negative binomial distribution. And our null hypothesis, k is equals to 10. And our one-tail test is either k is less than or equal to 10 or k is greater than or equal to 10. Depending on our situation, we'll have to make a decision. And if we concentrate on this alternative hypothesis, let us say this is k equals to 10 and less than or equal to 10, 78%, and greater than or equal to 10, 27%. So in either of the alternative hypotheses, we fail to reject the null because the area is k is less than or equal to 10, it covers 78% of the null, and k is greater than 10, it covers 27% of the null. So we fail to reject the null hypothesis. Now let us see another example where the nth success is 15 and k failures is 28 and probability of success is 50%. The graph nearly coincides with the normal distribution, and this region completely it belongs to this null. So this less than equal to we fail to reject the null, and greater than equal to 28, this portion it is only 2%. So maybe we can say that this region does not explain the property of this null area. So that is why we reject the null and we accept the alternative hypothesis, and this region is greater than 28. K is greater than or equal to 28 should be true. So this is the basics of hypothesis testing. Now let us see some of the usage of the negative binomial distribution. It is used to describe the distribution of count data, as for example, the parasites in the blood specimen, to model the number of parasites in the blood specimen, and used to describe the error distribution, especially again in the count data, and modeling the number of alcoholic drinks taken over a period of time, and modeling incidence rate of mastitis in cattle. And when the variance is greater than mean, negative binomial distribution is the appropriate distribution to explain it. And for accident statistics like birth death process in the psychological time series data of economics and medical, military, etc., the data says we use negative binomial distribution, and this is one of the example of negative binomial distribution. Even we have a negative binomial regression, which we will explore in some other time. And we see the negative binomial regression. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.